Hello there, my name is Emma Valent, and this is my third attempt at trying to figure out how long does it take to build an interstellar empire. So here's a little list of things we should know: our travel speed, the distance to our destination, preparation time, and what are we aiming for. So first, let's deal with preparation time. So, preparation time, what it is, it's the time you spend building and gearing up your ship, which may take about 5 to 10 years. Actually setting up a planet, I'm estimated about 50 years for a fairly advanced civilization, and then 2 models of spreading for our goals. Model A follows a hypothetical optimal path. What does that mean? It means that as we colonize each star system which we deem habitable to us, we follow a path that takes us exactly once through each star system. Basically colonizing one star at a time. In Model B, we do waves of expansion. That is, we colonize every habitable rock within a 10 light years radius, and then 20 light years, and then 30 light years, so on and so forth. Each one of these missions traveling even further than the one before. Before we jump to any other calculations, let's understand our local neighborhood. Around the Sun, for a sphere that's about 100 light years in radius, there lies about 14,000 bright stars, 76.5% of which are red dwarfs, with the other 23.5% being distributed across every other visible star in the night sky, since most red dwarfs are not really visible to the naked eye. However, from those 14,000 stars, only about 3,200 actually matter for us because they are the star type which is friendly to life. That means it doesn't emit a lot of ultraviolet light, doesn't emit a lot of infrared light. It lives long enough to allow the formation of planets and thus the maturing of the planet's surface in order to boil out some form of life. Basing off this data, we can use the square cube law to calculate the number of stars in any given volume of space, if we treat that volume of space as a multiple of our reference space. So a space that's twice the radius would have 8 times the volume, thus 8 times the number of stars. Likewise, a volume of space that's 4 times the radius would have 64 times the number of stars. So we take the number of stars from our reference space and then multiply by the radius of the new space in relation to the original radius and then cube it. Below here are 2 examples for the total number of stars: 14,000 by radius of 100 cubed, and then for stars friendly to life, 3,180 by the same thing cubed. To calculate the average distance between stars within this space, we take the volume, divide by the number of stars, and then cube root it. For a space 100 light years in radius, that's about 1,000,000 cubic light years divided by 4,000 and then cube rooted, that's 4.15 light years between stars. So far, that's all we need to start calculating the amount of time our Model A takes to conquer the whole volume of space we're talking about. As we just need the number of stars we're willing to colonize, the time it takes to do so, the average distance between those stars, and our traveled speed. In this example, considering only stars that are friendly to life, 50 years to colonize, then 6.8 light years of average distance, and then half the speed of light as our travel time, it would take about 200,000 years to colonize the whole of the stars that are friendly to life. It must be noted that even though we have 3,000 stars that are friendly to life, only about a fifth of them is expected to have a Earth-like planet around its habitable zone. And even so, it's not guaranteed to be 100% Earth-like. It could be a Venusian planet as well. And that would still technically count as an Earth-like planet. So even though we have a myriad of stars that are friendly to life, only a small percentage of them will actually be habitable or be inhabitable by some form of life. Now let's take a look at Model B. So if we subdivide our spherical region of space in thin enough shells, we are able to isolate stars and which find themselves at the same distance from our home planet. Through this, we can state that the time to reach any star within any radius d is less or equal to the time it takes to travel to that same distance d. For example, let's say we can travel at light speed and we want to travel to every planet between 10 and 20 light years away. No matter what planet we choose within this annular region around us, then it will take us between 10 and 20 years to reach any of them. Then, to know the number of stars in each of those shells, we multiply the number of stars in our reference space by the difference between the volumes of our final space and the initial space. Now, we need to have a low enough level of tolerance for the spacing between those shells. It's too much useless work to consider infinitely thin shells if the number of stars within that shell does not change at all. To have a significant difference between the number of stars from a shell to another, you want to have a spacing that matches the spacing between stars. To know the number of shells we need, we divide the total space radius by the tolerance level to get the number of shells. Then the total amount of time is given by the number of stars in your space multiplied by the number of years it takes to colonize each and one of them. And then we add everyone's favorite math element, series. And if it sounds complicated to you, you're absolutely right, unless you have access to an engineering calculator to do so. So after we simplify those series in a series of elements like these, where each of those C's amounts to the number of stars within each shell, you arrive to this beautiful solution that is like half as optimal as option A, which takes up about 800,000 years instead of 200,000. It is interesting to see how exponentially long it takes to get through each shell because, like in this example I drew here in the corner, for the first shell it only takes 2 travels. For the second shell, it takes 14 travels, and for the third shell, it takes 52 travels. So by the time we reach the third shell, we are taking 25 times more time than we took to colonize the first shell. Which, by the way, it's kind of horrible. Anyway, thanks for coming to my TED Talk.